Hi everyone, my name is Eric, the sales rep of Henkel Taiwan. Welcome to this channel. We share our technology, our expertise of adhesive bonding on this platform. This platform is run by the Henkel Taiwan. You are the most free welcome to leave your comment after watching this online seminar. Today's session is how to optimize the composite structural bonding. We have this presentation at PIDC last year. So today's session is a replicate of the last session at PIDC. Considering the volume of the message we are going to deliver in this session, we decided to divide this session into two parts. Part one will be the DOE, the design of experiment, to measure the bond strength of the composite structure. Specific focus on impact strength, not static strength. And in part two, we are going to collect the data we collected from the part one, and we are going to do the failure analysis to analyze the test result to come up with a conclusion, suggestion for engineer how to improve the design and then to achieve a better bonding quality without further increase of additional the material or the manufacturing cost. I think the composite material has been quite a hot topic because of it is essentially very light but very high structural strength. So we can see the use of the composite material has been expanded all kinds of industry. Specifically for some industry, they are looking for some lightweight, but they need a very high strength. For example, the sports vehicle or the transportation vehicle. Some of the key component has been used, replace the steel structure by the composite material. But anyhow, if we look at the slide over here, you can see that there are many things. I put a small circle here. That's the joint. No matter how good the individual composite material you can develop, you can have a very good quality of individual component, but eventually you still have to do the assembly. But we can understand, composite material, you can't do the welding, and also you do not want to drill a hole or put a mechanical fastener, because it's never been a good idea to drill a hole on the composite material because it just breaks overall strength. So we can do the assembly is using the bonding. You have to use adhesive. So adhesive becomes a very critical component, the critical success factor to all the design engineer. How you can achieve the overall structural integrity of your design. So it is not depends on the individual component of the quality, but also it depends on the bonding quality. If you can achieve a very good bonding quality to achieve the overall structural integrity. So now let's proceed to the next slide. For the bonding quality, so every design engineer is looking for the supplier of the adhesive. They have to provide some the bonding strength, the data of the adhesive they used. So if we look at this, the slide here, it is very popular, the test method to test the bond strength of the structural adhesive. So this is, sometimes we call a lab shear test. We use the specimen we bound together like the one on my hand. This is the things we bound here. You can bond any specimen. We have a well-known the STM, the spec or ISO, the standard test method. You can prepare this specimen very easily, and also you can bond like a steel or the aluminum specimen, no matter what kind of material. It's very easy to be prepared. And then we put onto the universal tensile tester to pull out from both ends, this end and this end. Later I will show you a video to measure the bond strength at this joint, Then the things come out that we understand this is a static strength, because in the universal tensile tester, the overhead will pull off the specimen slowly. So the data you can collect it is a static strength. It is not a dynamic strength or vibration or impact. This is the actual load applied to your structure, like a sports bike, like an aircraft, like any kinds of transportation vehicle. The loading applied to the product you design is never ever been a static one. So this data gives a challenge to the design engineer. You can't use this data. Even it is provided by the supplier, the data is not meaningful to your design. So this is the first challenge we introduce here. This is the dream of every engineer before I come out the first prototype of my design. I hope I can forecast to calculate the overall structural strength, because the prototype manufacture is cost money. So if we can figure out how strong the structure will be by the numerical analysis, that will be very helpful, can improve my design before I come out the first prototype. So the numerical design, numerical analysis, like a finite element showing on this slide, it has been widely well known to the industry. And it has been more than a few decades the successful application history. People can use the computer, the software to calculate the strength. So this is example. We find this paper this is a paper published a couple years ago. The research is analyzed things like this one. Going back to the slide, you can see that seeing the circle in red of the right-hand side of this slide, it is a numerical model, mathematical model they used to calculate the strength of the structure bounded by adhesive. The red color shown here is actually the adhesive layer. They cut it in the very fine mesh doing the finite element analysis. Either you apply the stress continuity or strain continuity to come out the stress analysis, the stress distribution of this bounding area to come out a overall strength projection. Unfortunately, the adhesive bounding is by no means a very even thickness. Actually, the bound line is something like this circle in black. It's on the left-hand side of this slide. This is actually bounding layer. So adhesive is being sitting in the irregular surface interface. Actually, all the mathematical model applied to adhesive bounding becomes not realistic. Result you calculate also cannot match with the test result. So come to this point, we understand composite material, the bounding, or even I can say for most of the adhesive bounding, you can't do the analysis by mathematical model. And also you can't use a static, very simple test to simulate the structural strength when dynamic loading is applied to the overall structure. So these two big challenges leads to a solution that leads direction to all design engineer. We need a test. We need a test to collect the data which is meaningful to our design. So let's take a look at the two videos I provided here. As you can see, the video on the left-hand side of this slide, it is a lab shear static strength measurement. For most of the adhesive supplier, they will provide this static strength data on the data sheet to our customer. The reason is very simple, because this is the easiest one, the test method in the lab, they can generate the data for our customer. But if you will design something, the load pattern is a dynamic one, the vibration, repeated loading, impact loading, I will advise you forget about this data on the data sheet. It doesn't mean anything for you. The right-hand side is actually a impact-dependent test. This is originally developed by some automotive maker, because everybody knows that automotive is driving on the road, all the load pattern is not static one. It's a vibration, it's repeated loading. You have your vehicle has to be survived on the road more than 10 years. Other than that, nobody is going to buy your car. Come to this point. This is a dynamic impact the test jig. Originally developed by some automotive maker, but now we can also find out in some STM spec like STM-D950, you can also find all these kind of impact tester. So in the part one, we have some Loctite in Taiwan. We also have some internal test method, which is very similar to the one we demonstrate on the right-hand side of this slide. So I'm going to introduce you to the test jig we are going to use in our DOE, the design of experiment. Let's take a look at this jig here. We have the specimen bounding, which is very similar to the lab shear test, the specimen we bound here. And then this specimen can be any of the substrate, like a forged aluminum alloy. It could be mild steel. It could be, of course, the main cast of today's session, the composite material. We bound the specimen and we put on the jig. And we use the pendulum to swing over here to hit the joint to deliver an impact energy to the joint. So we have done a calculation on the jig. So we have a predefined several the impact level here. We name it as the impact index. The impact index here. So if we can release the pendulum over here, we will deliver about 3.6 to 3.7 joule the energy into the joint. And then we increase the height of the pendulum, then we define its impact index 2. That can deliver more the impact energy to the joint. So you can refer to the slide to see that we totally define the 4 impact index. Based on the different index, we can define the impact strength of the joint, of this joint. So before we are going to proceed to the next slide, I can give you a very simple test, giving an idea how we do this impact test in our laboratory. We are going to do an impact test. Let's start from the impact index level 1. Okay, so it breaks, and please understand that maybe some people will say that, okay, this is only 3.6 joule, which is quite a small impact energy. But we have to understand the impact time is less than 0.1 second. So which means that the impact delivers a very significant energy in a very short period of time to break the joint. So actually the impact, the strength, the energy needed to break the joint is quite small compared with static strength. But anyhow, I also would like to take this chance to give you an idea how strong the steel structure will be. This is mild steel bounded by the same adhesive. But maybe you can take a look at. Again, this is level 1, nothing. Level 2, still remain intact. But we have to save some time, so let's move to the index level 4. Remain intact. So you might will ask why it makes so big the difference. Same adhesive, this is composite material, cannot survive in the index 1, impact index 1. This is steel structure. Seems that it's still very okay. Even no deformation. All right. So this gives us an evidence that the experience we learned from the steel bonding, learned from the aluminum alloy, forged aluminum, the test result cannot be applied to the composite material. When things come to the composite material, all the principle, the experience we learned before, we need to have some change. We have to change some the logic we learned from the previous experience. So that becomes today's the objective. We would like to develop something to create some DOE to collect the data, and then this is going to be explained in the part 2 of this session. I would like to introduce the composite material we use here. This composite material we use is just follow the industrial practice. That means that what the industry use, we just trying to match the spec of the composite material, such that the material, the data we generate can be used by our design engineer. This composite material, we are using the cross-lamination according to FAW 175 until it reached the thickness of 1.6 millimeter. And the dimension of the specimen is shown on the slide. As you can see, is about 25 millimeter times 114 millimeter length. So this is specimen. And on the top and the bottom there, we have a 45-degree lamination of the surface of the composite material. And before we do the bonding, we have the slight sandblasting to reach the surface roughness of 50 to 60 micrometer. These all trying to in line with the industrial practice. So how our customer, how our industry using the composite material, how do they prepare the composite material? We just follow the practice to make this specimen. Maybe you can see a small bottle, like 480, if I'm correct, shown on the picture, but this has nothing to do with today's session. It's just to give you an idea how big the specimen will be, okay? We just introduced the bonding, the test method, the testing jig, and we used to develop the DOE. And then the next one is that how we are going to select the adhesive. Again, we choose the adhesive which is widely used by the industry. We are not going to choose some very special one or some weird one. We pick up the adhesive used by the industry. Then all the adhesive, they have a totally different mechanical feature or chemical feature, but they are all being used by the industry. And every company, every design engineer, they have their logic to choose the different adhesive they preferred. And also they have also their methodology, their theory, why they go for this kind of adhesive. But anyhow, today we are going to put on the same platform, we are going to measure the physical, the feature of each adhesive by the same test method. We are not going to copy the data from the data sheet from different suppliers to create this table. So the table we're showing here is based on the same test method we do the test. So the data here will be a little bit different from the data shown on the data sheet. So in this spreadsheet, we measured the specific gravity to understand how much filler has been put into the adhesive. We measure the TG, the glass transition temperature, based on the DMA method to understand the TG, the difference. And also, we also measure the hardness, measure the elongation to break, and all these methods trying to figure out the special feature of the adhesive. And then when we come out with the test result, we understand for each kind of the test result, we are going to expect it, and then we can going back to see, okay, what kind of adhesive feature they can provide this kind of the result we are looking for. But instead of to explain this spreadsheet, because this spreadsheet is all numbers, so I like to give you a briefing how each candidate looks like. So there are totally 5 epoxy we've been collected. So we give them the code from the epoxy code 1 to epoxy code 5. So each code will represent a different feature of the adhesive. Like the epoxy code number 1, this is also very widely used. It is heat cured. Everything we put in the 1K means one component epoxy. It needs to be heat cured. When things are put in 2K, like code number 2, code number 3, there are 2K means there's 2 components. There's a room temperature, the AB part mixing, and then cured in room temperature. So every code then of the epoxy we choose here, they have a special feature like code 1 is a heat cure one, but epoxy number 1 is a very high exhaustion. So what is the exhaustion? I will explain in the part 2 of the session because it will have a lot of the impact to the bonding quality. So this is going to be presented in the section 2, part 2 of this session. And then we can look at the epoxy code number 2. This is low TG. Because most of the engineer, they are looking at the high TG system because the experience learned from the steel structural bonding, the high TG means that the adhesive can have a better the performance at elevated temperature. They can survive through the thermal cycle, the test. So we also including some of the low TG system to try to verify if this concept, this understanding is correct when we come to the composite material bonding. And also we can look at the code number 2 and number 3. They are both low TG system. But code number 3 also another very special feature. It's a very toughened material because more than 90% of the epoxy, the adhesive in the industry, they are very hard. This one, the number 3 candidate we choose, is very flexible. It's a toughened material. So we also would like to understand if toughened material can be very helpful to the impact the strength. And we proceed to the epoxy number 4. Number 4 is also the heat cured material, but the feature is low temperature curable. Why we choose this candidate? Because some of the customer, they have the limitation of the oven, the temperature of the oven cannot reach to some specific the level, or considering the productivity, the conveyor has to be moving very, very fast. So the adhesive, they do not have a long enough time to stay in the oven. So they need a fast cure, low temperature curable material, but they still want the physical, the bond strength. And the last candidate is a low exosome. Compared with candidate 1, everything is the same except the exosome. So we will also introduce in the part 2 how the exosome is going to impact the bonding quality of your design. Come to this point, we have completed the DOE explanation we developed here. We choose the pendulum to give an impact energy to the specimen. We developed the specimen according to industrial practice. That's the composite material, and also we're doing the surface preparation, doing the sandblasting, exactly followed industrial practice. And also we choose 5 epoxy covering the most of the candidate used by the industry, trying to understand every different feature of the epoxy, who can contribute to the final the impact strength of the material we are going to bond. So this comes to the end of this part. You are the most welcome to proceed to watch the part 2 of our session. And in the part 2 session, we will have the failure analysis and the data analysis of the data we collected from the part 1, the DOE, and also give you some of the advice and comments, suggestion to improve the bonding design. Thank you for your watching. Please feel free to leave your comment here, and we hope you enjoy our presentation. Thank you very much. Bye-bye.